Good afternoon, synthesists. Today we are looking at an infamous issue that affects a couple of different synthesizers, but the main one obviously being the Roland Juno-106, and infamously it has voice chips that fail over time, and this affects the Juno-106, the Juno-106S, as well as the Roland HS-60, and today we are going to show you how to replace the voice chips in any of those three synthesizers. So we will show you how to open up the synthesizer and also where the boards are placed inside, the circuit boards, because they all share the same circuit boards on the inside, but they are located in different areas due to the fact that there are speakers on either side on both the HS-60 and the Juno-106S. Okay, so the first step, as always, when you are going to work on a synthesizer like this, is to unplug it from mains power. I'm going to do this every time. Do not work on a synthesizer while it is plugged in unless you have the experience, the knowledge, and the ability to work in the instrument safely. But today we're going to simply start by unplugging it. And to open up the Juno-106, the 106S, and the HS-60, it's all the same process. So you'll notice on the side that there are 5 screws. You don't need to worry about the 3 on the bottom. All we're concerned about here is the 2 on the upper half of each end cap. Okay, so if you are working on a Juno-106, it's going to look just like this. You can see the power supply board here, the CPU board here, and the module board here. And this is the board that we're concerned with. We also have some panel boards up here as well. This one happens to be the jack board, but again, this is the board that we are concerned with, and this is where you will find it in the Juno-106. We will show you in just a minute where you can find this board in the Juno-106S and the HS-60. Basically, it will be hiding underneath the key bed here, because in those synthesizers, they had to make room for the speakers here and here, as well as another power supply for those speakers. The chips in question are these 6 here, 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 and here. These are those voice chips that handle your filter and amplifier sections for each voice on the Juno-106. And what happens over time is this resin coating on these chips deteriorates, becomes brittle, and even can become conductive in some cases, and that's why you end up with these chips failing. So we need to replace these. Today we're going to replace them in an HS-60, so now we're going to show you what it looks like on the inside of that synthesizer, but please understand that the process for any one of these 3 is the same. This board is the same, it's just in a different location. So the next thing that we need to do is remove this board so that we can get access to the underside to remove these voice chips. So now you can see we have the HS-60 here, which again shares the same analog synthesis circuitry as the Juno-106 and 106S, and we are going to replace all of the voice chips on this particular synthesizer, but we want to be able to show you how you can determine which voice chips are bad on your Juno-106 or HS-60, so that if you only want to replace 1 or 2 chips, you can determine which ones are bad. And it's pretty simple to do that. So to determine which voice chips are bad, you need to put the synthesizer into test mode. And this process is the same for any of the instruments we're talking about today. And you simply hold the key transpose button while you power it up, and you'll see that this pops up here. Once that happens, you need to hold poly 1 and poly 2 and pick a patch. But now when we press a note, you'll see the different number popping up, and this represents the voices as you swipe through them. So when we're listening here, you can tell that voice 1 works just fine. Voice 2 works, but it doesn't seem like the filter is functioning. Voice 3, same thing, it's working without the filter. Voice 4 sounds fine. Voice 5 and 6 aren't sounding at all. So we have 4 bad voice chips in this particular synthesizer, and we're just going to go ahead and replace all 6 of them with the Analog Renaissance Gravitational Slingshot chips. So the next thing we're going to do, as I make very clear, is power down the synthesizer and unplug it from mains. We do not want to open the synthesizer and work on it while it's plugged in for obvious safety reasons. So I'm just going to remove the cord and pull it away. We've already removed the 4 screws, one here, 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 and here. So when we open up the top panel, you'll see it is different than a Juno-106, but the 106S and the HS-60 will look like this. You can see here's the power supply for the actual audio circuitry, and this here is the power supply to power these speakers. And you can see the speakers are in pretty rough shape. The surrounds are all broken off and dried out. These are very easy to replace, and we'll put a link in the description for where you can buy new speakers for a very reasonable price, somewhere between $15 and $30. So the circuit board that we need to get to in the Juno-106S and in the HS-60 is underneath this key bed. Obviously there's a lot more going on in here as far as things that take up space, so Roland had to move the circuit board from right here to underneath the key bed. So next we're going to remove the key bed, and that's a fairly straightforward process. To do this, we need to access the underside of the synthesizer, and the best way I find to do that is to put it on a large flat surface and pull it out so that we can gain access to the underside to remove these screws. There's 3 more that we need to access from the top side. There's one here, and one here. So now that we've removed all 7 screws, you can see the key bed is loose, but to remove the key bed, it's actually plugged into a circuit board underneath here. So you're going to have to clip this zip tie right here. Be careful as you do it not to clip any of the wires. But then as we pull out the key bed, you'll see that it's plugged in right here and here. And as I've stated in earlier videos, you want to be safe about how they go back. Some manufacturers label them, but it's very easy to just come in and make a mark on one of them so that you can know that you're sure when you match it back up that you put it back where it went before. And to remove the plugs, simply grab as firmly as possible and pull straight out. You may have to wiggle back and forth a little bit, but now we've removed our key bed. So now that we've removed the key bed, you can see underneath it, and you can see that they're the exact same boards that you find in the Juno-106. They're just in a different location. You can see it actually says Roland Juno-106 here and as well on the CPU board. But again, this is the board that we have to work on today because these 6 voice chips here are have either failed or are in the process of failing. Next, we're going to remove this board. And to be safe, I'm going to ground myself as I do it. Again, static electricity can cause problems. First thing we need to do is remove these screws here. There are a total of 6 of them. So I'm going to go through with my screwdriver and simply remove all of them. When you remove screws, as I mentioned in the last video, you want to place them together in sections so that you know where they go back. And as I've done previously, I'm going to make some marks on these connectors so that I'm sure they go back in the right location. Roland is pretty good about making sure that you don't have 2 connectors with the same number of pins. You can see that they did that here. They used a larger connector and didn't use one of the cables here just to make it easier to know again where they go back, but I just like to be 100% sure whenever there's 2 connectors that are right next to each other. So I'm going to remove these connections. And now we're able to remove the circuit board. Before I take the voice board out, I just want to go over a couple of things and do a quick overview of what everything is doing here in this synthesizer. As I mentioned earlier, this is the power supply for the synthesizer itself. This is the power supply and amplifier for the speakers. This here is the CPU board, and this is the exact same CPU board you'd find in a Juno-106. It actually says Juno-106 on it. Same thing here with the module or voice board. It actually says Juno-106, so these are not unique to the HS-60. They are shared in the HS-60, the Juno-106, and the 106S. The only major differences, again, are the locations, and then the jack boards and panel boards up here. This is the jack board, but it also contains your chorus circuit. You can see those right here, these MN3009 chorus chips. Bucket Brigade delays are what they are, but that also encompasses your jacks as well. And if you're wondering about when the synthesizer was made, you can look it up based on the serial number, but there's a really easy way to get a good general idea when you have the synthesizer open. And that is simply looking at the date codes on the chips. And they're not all going to be exactly the same because they are the date code as to when that chip was manufactured. But by looking at a few of them, you can get a good idea as to the time frame that your synthesizer was built. And if you simply look close on these chips here, you'll see on this one, for example, it says 8510. And what that means is that this chip was made in the 10th week of 1985. If we look at a different one here, this one says 8427. So this chip was made in the 27th week of 1984. And I found one earlier, there's one right here actually, this one says 8607, so this chip was made in the 7th week of 1986. So we know that this chip, or this synthesizer, must have been made after the 7th week of 1986, and you get a general idea that it's going to be somewhere around the first half of 1986 that this particular synthesizer was built. And when you're looking at this, as far as the audio signal path, obviously the CPU board is here, and you have more memory sections, but this is your voice section right here. And each one of these chips makes up your filter, but the combination of everything here is your oscillator, your amplifiers, your envelopes, and the filters. All of that sort of thing is contained right in here. All of these are trimmer pots that allow you to calibrate the synthesizer. I highly recommend not touching those at all while you remove these. You may have to do some calibration after you replace the chips, but by default, it's best to leave them as is until you know you need to make an adjustment. Next, we're going to remove the actual voice or module board, but I neglected to mention earlier that there is one more screw, a 7th screw that's connected to this ground right here, so you need to make sure you remove that as well. And this is a smaller screw than the other 6, so please make note of that. It needs to go back in the same location. But to remove the board, you can now just simply lift it out. And this is our business board. And the Juno-106 and HS-60, this is what you actually synthesizes the sound, the audio that you hear when you're playing it. So we now have the voice or module board out by itself so that we can work on it, because again, we need to gain access to the underside of these 6 chips so that we can remove them to replace them with the upgraded chips. So I'm simply going to flip the board over, and you can see here where these chips are located, here, 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 and here. And normally what I would do to remove this is I would use some flux and my solder gun here, and this is basically a solder vacuum where the tip heats up the solder and then it sucks it in to here, and it's much faster and it's just a more efficient way of doing things, but these are expensive. The goal of our channel here is to help you guys do this sort of work with accessible tools, so we're not going to use this today. So next I'm going to talk about the tools that I am going to use to desolder these chips. And if you've never soldered before, this is not a job I would recommend you start with. But if you have some basic soldering experience, it should be something that you can do as long as you take your time, you're patient. One of my biggest rules for myself is that if I'm in a hurry, or if I get frustrated, I stop working. Because if you try to speed through this, or you get frustrated, you could very likely end up causing damage to the circuit board. So the next thing I want to mention, or tool I want to discuss, is this here. And this is a hand vacuum solder pump. And you basically push the plunger down, and you bring in your soldering iron, you get the joint molten, and then you bring this over and it will suck the solder out. I don't recommend using these, especially if you are a beginner. I'm going to show you another option in a minute that I feel is safer and overall just a better way to do it, because when you push these down, there's a spring in there, and when you release that tension, again, it has a tendency to jump on that board, and you really don't want to have any potential of causing damage to this board as you work on it. So now I'm going to show you the tools that are necessary and that I do recommend you use. As far as a soldering iron, almost any will do. I prefer to use this Weller soldering iron. It's very reliable. It has adjustable temperature. But one thing that you may not know about is that the tip that you use is very important. I prefer these beveled tips. There are also conical tips, which are basically just come to a point. There are also chisel tips, but I prefer these beveled tips that are basically cut off at an angle because it allows you to apply a very good solid amount of heat to the joint as you're working on it. So now that I've talked about the soldering iron, we need to talk about the other things that are very important that you have when you're doing work like this. Number one, again, isopropyl rubbing alcohol. As high a percentage as you can get. It's what you'll use to clean the board, both before, during, and after you do this work. You also need some solder wick. This is my preferred method to remove solder at a reasonable cost. You also need flux. All three of these are different types of flux, but flux is probably the number one thing that beginners may not be familiar with, but it's incredibly important that you use flux whenever you're soldering or desoldering. It will result in you having much cleaner joints, as well as not having the solder ball up or not easily adhere to the pad that you're trying to solder it to. And then finally, obviously, we need solder itself. 60-40 ratio is the common one to use. And when you're buying all these products, don't buy the cheapest option. It really makes a difference if you buy quality wick or in addition to the flux itself and the solder itself. You'll also want some of these swabs, as I've used in the last video, as you're cleaning and working through the steps of desoldering the chips from the board. So next we are going to start to remove the voice chips by desoldering the pins on the underside of the board. And I want to start by saying that this is probably the most difficult part of this job and where the most care and patience needs to be taken, because you need to make sure that all of the solder is removed from every pin before you start to try and remove it from the other side of the board, the chip itself. If you are trying to remove the chip and it's still stuck in there firm, you want to make sure you go back and attempt to remove the solder even more. The chip itself should come out very easily. If you're pulling on it, and you shouldn't have to, because if you're pulling on it, there's still solder there, and if you pull too hard, you may end up ripping out a pad or even a trace itself. So we've cleaned this area here. You want to make sure that it's clean before you start. Again, we're going to desolder all 6 chips here, 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 and here. And so what I'm going to do is I'm going to start by getting some flux on a little swab, and then I'm going to run it down the whole length of each line of pins. Dab some of it here and here, so go back, but you want to make sure you have a really nice coverage of flux on all the pins before you start. Do not underestimate the importance of using flux. If you do try to do this without it, you are going to have problems. It is one of the biggest pointers that I can give you. Do not attempt to solder or desolder something like this without using plenty of flux. Reapply as often as you'd like. And in between steps, you want to make sure that you clean with swabs and rubbing alcohol. So as I mentioned earlier, flux, rubbing alcohol, and quality solder wick or solder braid is my preferred way to remove chips like this. And to do it, you simply take your soldering iron and make sure that your tip is clean and you have it at the correct temperature. But you simply bring your wick in next to each joint, and you're going to come in and press somewhat firmly against it. One thing to be sure of is you do not want to hold your soldering iron on the board for really extended periods of time. If you don't think all the solder has been removed from that area, pull the soldering iron away and come back at it again. You don't want to be putting too much heat on these boards as you do this. So again, I just come in. The goal when you're soldering is to touch the tip to the pin itself that you're actually trying to desolder from. So I get the braid nice and close, and I bring it up, and you can see on the braid itself that it has absorbed some of the solder there. And we're just going to have to go back and forth on this until we remove all of it. So one really big point I need to make is that you need to have active ventilation and good airflow when you are doing this. This is lead solder that we are removing right now. It is absolutely harmful to be breathing. It's out of frame, but we have a ventilation fan pulling the air out of this area. You do not want to be breathing in the smoke that comes off of this. So again, I'm just going to take my wick, and this time I'm going to come in from the other side. I'm going to bring it in nice and close. I look to push it up flat next to the pin itself, then come in and let it absorb the flux there, or I'm sorry, the solder. I'm just going to move down the line. Again, do not apply too much heat as you do this. Okay, so I wanted to show you something up close here, and as you can see, it looks like I've removed most of the solder from this particular chip here, and I want to test to see if that's in fact true. So if I simply wiggle the chip from the underside, if you look closely, you'll be able to see that some of the pins are moving freely, but that there are a few of them that are not moving at all, and that's telling us we have not removed all the solder. All the pins need to be able to move freely. Do not try to use force as you remove this chip. So at this point, you can also see that most of our flux has melted or burned away. So I'm also going to come in and add more flux. And then again, I'm going to come in and see which pins are not wiggling and desolder those accordingly. Okay, so I just want to show you now that I've gone through and thoroughly removed all the solder from each pin, and as you can see, as I wiggle it, every single pin is moving back and forth, and therefore I know it's free inside the through hole, and you'll be able to remove the chip accordingly. Now that I've shown you how to remove one of the chips using flux and solder braid, in an effort to save time, I'm going to use the desoldering gun to remove the rest, but I will still likely have to come back in with some solder braid even after going through this, again, to ensure that all the pins are loose before I start to try and remove the chip. If the chip is not coming out easily, you need to go back and figure out which pin still has solder on it. Okay, so now that we've removed all of our voice chips, I'm going to go through and clean the pads where these were before we solder in the new chips. So I'm again just going to take some rubbing alcohol and go through and remove both the flux that I just added to remove the chips themselves and the flux that had been left there from when this board was heat flow soldered at the factory. You want to clean in between each step if possible. When you're resoldering, these pads need to be clean in order for the solder to want to really solidly make a connection. So don't leave all the old flux and dirt on the boards. Make sure you clean in between this step. So the next thing we're going to do is install the new Analog Renaissance Gravitational Slingshot chips. You can see them here versus the original Roland 80017A voice chips. And so what we've done is we've made sure that all of the solder is removed from every through hole on the board, and we've cleaned both sides, both top and bottom. You want to make sure again that this is clean and that the through holes are clean, otherwise the solder is not going to adhere to it properly. So we're just going to place one in each terminal, and you can't get this wrong because there's a pin missing here, so you cannot put them in backwards. So don't worry about that, just make sure that they go into the proper location. So now that we've put the chips in, we need to flip the board over to gain access to the other side so we can solder them in. But we want to make sure that they stay in their positions firmly and don't fall out. And if you've removed all the solder properly like I went through, they should easily come out. So what I do is I grab a little length of painter's tape, and I will just place it here over those chips and flip it around the other side. Make sure it's nice and snug. Oopsie, one came out there already. Nice and snug. And then I'll fold this over the other side. And that way I know that when I flip the board over, the chips are going to stay in place and I have access to solder them in without worrying about them moving or changing position. Okay, so we've made sure that the board is clean here. We've installed the new chips from the underside. Now, once again, I'm going to add a good amount of flux onto each row of pins so that we can ensure that we have nice, quality, long-lasting, reliable solder joints. I cannot emphasize it enough how much better your solder joints will be if you use flux and clean the board whenever necessary as you go through and do stuff like this. Now we are actually going to solder these chips in place. We've made sure that they're positioned correctly from the underside. We've held that down with tape, and we've put a nice gob of flux on every pin. Again, that's very important. And now I'm just going to take my soldering iron, make sure that the tip is clean, and I'm going to come in here. And you want to apply the heat directly to the pin itself. You don't want to put the solder on the end of the tip and then apply it that way. So I'm going to apply heat here, and I'm just going to bring in the solder. It just takes 1 second to get it going here. Again, don't leave your soldering iron on the pin for too long. Now that I've soldered in all 6 chips, I'm going to clean the bottom of this board again. I want to be able to see each joint up close and clearly so that I can make sure that the solder has properly seated and that there aren't any pins that are connected or bridged to another pin on accident. So once again, I'm just going to come in with some rubbing alcohol and get all of this flux out of here so I can take a good and clear look at the joints themselves before we reinstall the board. One of the things that I do as a final step in cleaning the bottom of these boards, or you could really do it at any point, smart to do it in the beginning, is I simply take the board and I hold it over the sink, and I have this spray bottle which is filled with, again, 99% rubbing alcohol. And you can simply hold it over the sink, bring the spray nozzle up close, and really spray in there and let all that rubbing alcohol drag all the flux down, and it'll drip off into your sink, and you'll end up with a board that's extremely clean on the bottom, just like this. So if you plan on doing this sort of thing more than once, it's a good investment to have just a little spray bottle filled with rubbing alcohol. Okay, so now that we have finished installing the new voice chips and we are sure that there's no connections between the pins that there shouldn't be and the board is clean, we're simply going to take the board itself and place it back into the position it was in when we first opened up the synth, and you can see how clean the board is, and we've gone through and double checked everything. So we're just going to slide the board back in, line up the hole positions, and the first thing I'm going to put back in is the ground. It's the last thing I took out. Keep in mind that these are being screwed into wood, so you do not want to over tighten them, otherwise you'll simply strip it. On all these Rolands, they usually don't use, you know, a solid piece of wood. It's usually particle board of some sort, so don't overturn it, otherwise you're just going to end up stripping the hole that it goes down into. Just make sure it's firmly snug down in its position. Okay, once again, I'm just going to make sure that the marks match up to where I placed them when we took the board out. Otherwise, the location of the connection itself should tell you where it connects, but you want to put it in properly. Make sure it's seated well and that it's not off to one side. Okay, so the last thing we're going to do is just to give you guys a little rundown, an introduction, a taste on how to calibrate a synthesizer like this. Because when you do a modification as significant as replacing the filter chips with an aftermarket filter chip, we need to make sure that we make any adjustments that the manufacturer calls for, but also that this new circuitry isn't making isn't pulling anything out of whack as far as calibration is concerned. And so I'm going to follow along the Roland Juno-106 service notes today, and I'm going to show you how to make sure that the power supply is calibrated properly, and then we're going to go in and do some basic calibration for the voices down here on the module board. We're going to start with the power supply. And as I've mentioned in the first few videos at the beginning so far, you don't ever want to have a synthesizer plugged in or powered on while you have it open and are working on it. But once you get to this point, it's an absolute necessity. You cannot check the power supply DC voltage rails with, and check their levels without having the synthesizer powered on. But you really want to make sure that you only have the synthesizer plugged in and powered on when you are doing these calibration processes, and not while you are working on it, again, for safety's sake. So in order to test the power supply, we're going to follow along with the service notes, which I have up on my computer screen over here out of frame. But we're going to start by simply turning the synthesizer on. I always like to make sure that there's no tools left over or anything that I could end up shorting or causing any issues, because again, we want to be as careful as possible while we have it plugged in and turned on. So I'm going to go ahead and turn the synthesizer on, and I'm going to turn my voltmeter on here. You can see I have it set to volts DC, and the first step in the DC supply voltage power supply calibration process is it wants us to adjust VR1 for negative 15 volts plus or minus 10 millivolts at location A. We're specifically looking at this power supply here right now, and we need to look at location A, which is marked on the diagram right over here. The schematics, it refers to point A right here, and it's actually marked on the circuit board. You can see this diode here is marked ground on one side over here, and it's marked TP1 for test point 1 on the other side, and it's marked negative 15 volts. So we know that that is the test point where we're going to check to see if this is accurately running its negative 15 volt power supply rail. So I'm going to grab my probes, and Roland again was nice, they marked everything, so I'm going to stick my ground on one side over here, and I'm going to stick my positive on the other side, and we're going to look at our voltage here, and you can see it's spot on, reading at negative 15.01 volts, which is, it does not have to be perfectly spot on. Remember, the service notes themselves said within plus or minus 10 millivolts, so we're within just 1 millivolt, so we're absolutely fine there on the first test point A, or test point 1, which is the negative 15 volt supply rail. If it was not accurate, we would adjust VR1 right here, which is also labeled, to bring it closer to that negative 15 volt supply rail that we're looking for. The next step it tells us to look at is at location B, and here we are going to adjust VR2. VR stands for variable resistor. We're going to adjust VR2 for plus 5 volts, again within a 10 millivolt range at location B. So let's find location B on the board here, and you can see it's marked as test point number 2, the 5 volt rail right here. So again, I'm going to find my ground, and again, Roland did a great job to mark everything, and so I can see on all these pins here where ground is, and so I know ground is in this pin right here, and then I can look, I can probe test point 2, and we'll see if we look at our meter right here, it's running at exactly 4.98 millivolts. So we're within 0.2 millivolts of the 5 volt positive rail that we're looking for. So that as well is also within spec. Third step is we are going to verify that plus 15 volts at test point C or test point 3. And when it says verify, it's just asking you to make sure that it's as close as possible. If it doesn't say adjust VR1 or VR2, that means there is no adjustment trimmer for that particular voltage rail on this power supply. We just want to make sure that our plus 15 volt rail is close to plus 15 volts within tolerance, because if it's not, then we have a problem. There is no way to adjust it. That's built into the power supply itself. So I'm going to find test point C or test point 3 based on the schematics and the service notes that I'm looking at right now. I'm again going to go ahead and stick my negative probe in the ground, and then here is test point number 3, and if we look right here on my voltmeter, you see it's 15.31 volts. And the tolerance for this one is plus or minus 0.8 volts. And we are only outside of 15 volts by 0.3 volts. So again, this is absolutely within spec, and that is totally fine. And the last one it's asking us to check is that we verify the plus 5 volt rail within plus or minus half a volt at test point D or test point number 4, which is right up here. So I'm going to go ahead and probe that one as well. And look at that, right on the money, 5 volts exactly. So of course, obviously that is fine as well. So on this particular power supply, there is no adjustments to make, because it's all within spec based on the manufacturer's recommendations. According to the service notes, step number 2, we are going to check the DCO CV offset. And again, it's asking us to use a voltmeter, so I still have that set up right here. And it wants us to, and for these, just so you know, for these steps, we have the synth in test mode, which involves holding the key transpose button while you power it on. Once that's done, the service notes will tell you to put it in certain modes. Like in this one, it wants it in poly 1 mode, which I have selected, and then it asks us to press the MIDI channel, because in this calibration process, when you do that, it sets up so that it reads 0 volts. So that's what we're looking for right now. It's telling us to look at test point number 3, and I can see test point number 3 right here on the module board. So I'm gonna go and find the ground point right over here, and then I'm gonna probe for test point 3, and it's asking us to see if it shows 0 volts, and sure enough, we are at 0 volts on the dot for step number 2, which is exactly where we want to be at. So we're going to go ahead and leave that there. Okay, step number 3, according to service notes, we're going to be checking the VCA bias. It's asking us to use a voltmeter to check test point number 7 in poly 1 mode. Again, we've got to push MIDI channel just to make sure it's set properly. And we are going to probe test point 7 and adjust variable resistor number 34 if necessary to make sure that it's reading between plus 0.25 volts and plus 0.27 volts. So here we are. I'm going to find test point 7, which I can see right here. And again, I'm going to put my negative probe on the ground, check test point 7, and look at my meter. And sure enough, we are within spec. Remember, it told us to make sure it's between 0.25 and 0.27, and we are at 0.262, so we are right on the money. If we were not, we would adjust VR34 to get it right back within range. Okay, step number 4 of the calibration process is having us check the VCA offset. And you have to do this for each voice. For purposes of saving time, we're just going to show you the process for one voice on each step just because it's the same for each one. And so in this mode, it's asking us to use an oscilloscope to check test points 8 through 13, which is one for each voice, each test point. And it wants us in bank number 1 and in poly 1 mode. So I am going to go ahead and probe one of these test points, and it's asking us to make sure that we see as few bumps as possible. So let's see what bumps we're seeing. Oh, and there you can see them. Get a good signal here. You can see them passing there. So you can see that's definitely not calibrated because we want to see a flat, straight line there. So I'm going to go ahead and make adjustments. There's a nice photo or diagram in the service manual for this, so you can see. Now you can see I've got it pretty much flat here, and that's what we're looking for, as we want to get it as flat as possible. Okay, so the next step is step number 5, and we are checking the VCF resonance. It's asking us to use an oscilloscope to check test points 14 through 19, 19 being voice 1, 14 being voice 6, in poly 1 mode on bank number 3. And so we're set properly there. It's asking us to hold down key number C4, which on this keyboard is actually here. It looks like the third one, but you got to remember there's an octave down here on a piano or a full 88 key instrument. So we're going to hold down C4 right here using this little piece of metal, whatever you want to call it. And right now we are looking at test point number 15, which, and again in this case we're just going to show you one voice. Test point number 15 corresponds with voice number 5, and voice number 5 corresponds with variable resistor number 6 according to the schematic. So we are going to look at this, and it tells us to adjust it for 4.8 volts peak to peak. And if we're looking at the oscilloscope, peak to peak is simply from the bottom tip of the waveform to the top tip. And if you look on my my oscilloscope here, it's telling us that we are set to 2.72 volts peak to peak when we are looking for 4.8. So I'm going to adjust variable resistor number 6, which if I'm not mistaken is right up here. And as I adjust it, if we look at the oscilloscope, you'll see it change. Up, went down, we're going to go up. We want to find 4.8 volts, and you'll see the peaks increasing. Oh, we're at 4.5, 4.6, 4.7, and 4.8, 4.9, a little big there. I'm going to go back down. We are at almost 4.8 exactly there. So we've now just calibrated voice number 5 at 4.8 volts peak to peak. Okay, we're now on step number 6, which we're going to be checking the VCA gain. And again, it wants us to use an oscilloscope to check test points 8 through 13, which is voices number 1 through 6 again, in poly 1 mode on bank 3. Again, we need to hold down key C4, and you can see I've already got my probe set up here, and it's telling us to set these to 6 volts peak to peak, and we are currently reading 5.52. So we need to make an adjustment, and right now I am currently on test point number 10, which corresponds with voice number 3. And voice number 3 corresponds with the variable resistor number 17. So I'm going to adjust VR17 right here for 6 volts peak to peak. Up, we're going. We were at 5.4. We're now at 5.8, 5.9, and 6 volts right on the money. Okay, next we are going to be looking at step number 7, which is VCF frequency, and it simply wants us to test each voice to make sure that when we're holding down the C4 key that it is we're reading 248 hertz for the pitch of B3. So right now we're looking at voice number 3, which is VR variable resistor number 19, and it wants us to, again, have it at 248 hertz. If I look at my oscilloscope, we're reading 264 hertz. Sorry if that's a little small to see, but we need to go ahead and make an adjustment, in this case to VR number 19. And 249. 247, 248. Okay, so next step is step 8, and we're kind of looking at the opposite end here. Steps 7 and 8 are related, but we're looking at the same voice. Instead of holding key C4, we're now holding key 6, or C6, excuse me. And we want to make sure that this is tuned to 992 hertz, if I'm not mistaken. Yes, that is correct. Or pitch of B5, and right now we are reading 961, so we're a little low. So it says that voice 3 is adjusted with VR number 18, which I'm going to come in and find right here. And I'm going to adjust this to 992 from 961. So let's see here. 980. 990. Okay, next step is step number 9, and now we're going to be looking at noise and noise level, and it's asking us to use an oscilloscope to check test point 8 in poly 1 mode, and we're going to hold down any key and adjust variable resistor number 32 for 4 volts peak to peak on the oscilloscope. So I'm just going to hold down any key, and I'll just go ahead and push auto on my oscilloscope so you can see it a little bit better here. And give it a second. We're going to go ahead and adjust VR32 here. And right now we're at 4.6 volts. I'm coming down 4.2, 4 volts peak to peak. Okay, next is step number 10, second to last step, and we're going to be looking at the duty cycle of the pulse wave. And so it is asking us to go ahead and use an oscilloscope to check test points 8 through 13 in poly 1 mode on bank number 5. And we are going to be holding down the C4 key as we already have held down. And we're going to look at the scope, and we want to make sure that our duty cycle is set between 48 and 52 hertz. Excuse me, percent. 48 and 52%. You can see right here, it's already looking very close because this spaces, as far as the width is similar on both, and I can read here the duty cycle is set to 48.42 hertz. So we need to adjust that a little bit. Technically it's within spec, but I think I can get a little closer. 50.53 went a little over. 49.47. Looks like it's jumping right in between those two, so we're going to get as close as we can at 50.53. Okay, so the last steps of the calibration process involve checking a couple of things on the jack board, including the chorus and the load offset. We haven't made any changes to that, and it's sounding just fine, and it's not as super relevant to what we've done here today in changing the voice chips, so we're going to leave that as is, and I'm going to go ahead and put the synthesizer back together now.